the voltage source VThevenin and the resistance RThevenin. Norton's theorem. We know that every voltage source with a series internal resistance has a current source equivalent. The current source equivalent can be determined by Norton's theorem. According to the theorem, any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a current source and a parallel resistor as shown below. The Norton's resistance Rn is basically equal to the Thevenin resistance Rth, and the current source In is basically equal to E Thevenin by R Thevenin. Norton's theorem. Now, in order to determine the Norton's equivalent circuit, we have to follow the same procedures as we did to determine the Thevenin equivalent circuit. That is, at first we need to remove the load resistance, then mark the terminals. After that, we need to determine the Norton equivalent resistance, which is basically equal to the Thevenin's equivalent resistance Rth. In order to do that, we need to set all the sources equal to 0. In Thevenin's equivalent network, the Thevenin voltage is basically equal to the open circuit voltage between the marked terminals. In this case, the Norton current, that is I Norton, is basically the short circuit current between the marked terminals. The final step is to draw the Norton equivalent network, that is the current source and the Norton resistance connected in parallel, and with that to connect the load which was initially removed from the original circuit. The Norton and Thevenin equivalent circuits can be found from each other as well by using source transformation. That is, E Thevenin and R Thevenin can be replaced with In and Rn using source transformation. Problem 9. Find the Norton equivalent circuit for the network in the shaded region. That is, we have to determine the Norton equivalent circuit for this portion of the network. The first step is to remove the load resistance RL and deactivate the voltage source E. We deactivate the voltage source with its short circuit equivalent. Then we determine Rn, which is basically equals to R Thevenin. In this case, Rn is equal to 2 ohm. The next step is to determine the Norton equivalent current, that is In. In order to do that, we replace the voltage source and we connect terminal A and B with a wire. That is, we short them. And then we determine the current flowing through this wire, which is basically In. In this case, In will be equal to 3 ampere. The final step is to draw the Norton equivalent network along with the load resistance, which was removed at the first stage. It is possible to convert from Norton's equivalent circuit to Thevenin's equivalent circuit and vice versa using source conversion theorem. In case of Norton's equivalent circuit, the Norton's resistance Rn must be connected in parallel with the Norton's current source In. Whereas in the Thevenin's equivalent network, the Thevenin resistance Rth must be connected in series with the voltage source E Thevenin. Problem 10. Find the Norton equivalent circuit for the given network. That is, for this network over here, we need to determine the Norton equivalent network. In order to determine the Norton equivalent network, we need to find the Norton equivalent resistance Rn and the short circuit current between terminals A and B, which will be In. In order to determine the Norton equivalent resistance Rn, we need to deactivate the independent sources. The voltage source of 12 volt must be replaced by a short circuit equivalent, and the current source of 2 ampere must be replaced with an open circuit equivalent. Then we can determine the Norton equivalent resistance Rin. In order to determine the Norton equivalent current, that is I Norton, when we connect a wire between terminal A and B, then you can observe that this resistor of 5 ohm resistance is basically shorted by this wire. Hence, no current will flow through this resistor. That is, the current flowing through the resistor will be equal to 0. Thus, by applying mesh analysis, we can easily determine the short circuit current, that is In, which will be equal to I2. The Norton equivalent current or the Norton current In will be equal to 1 ampere. Another way to determine the Norton equivalent current or the Norton current In is to determine the open circuit voltage VOC and then divide the open circuit voltage VOC with the Norton resistance Rin. Whichever way you use, the Norton equivalent current will be equal to 1 ampere. In this example, we have an independent voltage source and a dependent current source. To find Rn, we set the independent voltage source equal to 0 by replacing it with the short circuit equivalent. The same cannot be done for the dependent source. Hence, we connect a voltage source of 1 volt across the terminals A and B. On deactivating the voltage source by this short circuit equivalent, the 4 ohm resistor has also been shorted. Hence, Ix becomes equal to 0. The value of the dependent current source is based on Ix. Since Ix equals to 0, therefore, this value of 2Ix also becomes equals to 0. And the current flowing through the voltage source I0 is equal to 0.2 ampere. Using the value of this current and the voltage, we can determine the Norton's resistance, which is Rn equals to V0 by I0 equals 5 ohm. In order to determine the short circuit current, which is In, we reconnect the voltage source. Note from this figure that the 4 ohm resistor and the 10 volt source and the 5 ohm resistor and the dependent source are in parallel. Hence, Ix will be equal to 10 by 4, which is 2.5 ampere. At note A, KCL gives I short circuit, which is equal to 10 by 5 plus 2Ix, that is 7 ampere. So In is basically equal to 7 ampere. Maximum power transfer theorem. Using the Thevenin equivalent network, it is possible to determine the value of the load at which the load will receive maximum power from the network. Through experiments, it has been found that the load will receive maximum power at a value which is equal to the Thevenin resistance of the network. That is, when RL will be equal to R Thevenin, RL will receive maximum power from the network. If we consider this network over here, then the shaded region represents the Thevenin equivalent circuit and over here we have a variable load RL connected. RL and RThevenin are connected in series. Therefore, if we want to determine the current flowing through RL, then according to Ohm's law, IL will be equal to E Thevenin by RThevenin plus RL. Now, from experiments, it has been found that RL will receive a maximum power when the value of RL is equal to the value of RThevenin. Hence, if we substitute the value of RL as RThevenin in this expression, we will get that at maximum power delivery from the network, IL will be equal to E Thevenin divided by 2 RThevenin. So, if we substitute this expression in the formula for maximum power, that is PL equals IL square by RL, then it will be equal to E Thevenin square divided by 4 R Thevenin. So, the expression for the maximum power delivered to the load is equal to E Thevenin square divided by 4 R Thevenin. Using the Thevenin equivalent network, it has been experimentally determined that RL will receive maximum power from the network when its value is equal to RThevenin. That is, when RL equals to RThevenin, the power across the load will be maximum. However, if the load applied, that is the value of RL is less than the Thevenin resistance, then the power will drop off rapidly as it gets smaller. However, if the load applied is greater than the Thevenin resistance, that is RL is greater than RThevenin, then the power will also drop off, but at a much lower rate. Under maximum conditions, only half the power delivered by the source gets to the load. Now that sounds disastrous, but remember that we are starting out with a fixed Thevenin voltage and resistance, and the above simply tells us that we must make the two resistance levels equal if we want maximum power to the load. On an efficiency basis, we are working at only 50% level, but we are content because we are getting maximum power output of our system. Efficiency is basically equal to the power delivered to the load divided by the power delivered by the source times 100%. In this example, we have to find the value of RL for maximum power transfer in the circuit, and we also have to determine the maximum power. That is, first of all, we need to determine the value of RL for which it will receive maximum power from the source, and then we also need to determine that maximum power value. So, we know that RL will receive maximum power when its value is equals to RThevenin, and in order to determine PL max, we also need to know the E Thevenin value. Hence, in order to determine RThevenin, at first we need to remove RL from the network and deactivate all the sources. This is how the network will look. So, RThevenin is equal to 9 ohm, which means that RL will also be equal to 9 ohm. Now, in order to determine VThevenin, which is the open circuit voltage, we reconnect the sources as it was in the original network. Then we determine this open circuit voltage. Since these 2 points are floating, therefore no current will flow through this resistor. Hence, the potential drop across the 2 ohm resistor will be equal to 0. Therefore, VThevenin, which is the open circuit voltage, will be equal to the voltage drop across the 2 ampere current source. Using mesh analysis, we can determine the currents I1 and I2, and then applying KVL, we can determine VThevenin, which will be equal to 22 volt. We know that VThevenin is equal to 22 volts and RL is equal to 9 ohm. Hence, P max will be equal to VThevenin square divided by 4RL, which is equal to 13.44 watt.